ये है हापुड़ स्थित धौलाना में CIDC यानी कंस्ट्रक्शन इंडस्ट्री डेवलपमेंट काउंसिल का कौशल विकास केंद्र। और अपनी तकदीर बदलने के लिए कड़ी धूप में मशक्कत करते ये बच्चे, इन सब का सपना है।
Good morning, good afternoon, or good night. Local time is right now. I am happy and honored to share with you this presentation, Technological Acceleration of the Ready-Mix Concrete Industry Due to the COVID-19 Pandemic, Our Story, the Guatemalan Experience. And to begin with, Guatemala and India, we live far, far away. We are not less than 15,000 kilometers apart from India. For sure, more than 24 hours flying from one place to another. For sure, different customs, different traditions, but unified by concrete. Elaborating concrete, that's done probably the same way anywhere. So Central America is that tiny piece of land between North and South America, the Central American Isthmus. You could see here Mexico and Colombia, these little 6-7 nations that conform the Central American Isthmus is very, very small. And so tiny, so small that a storm, in this case, the latest storm, Iota, that hit us just 2 weeks ago and covered the entire Central American Isthmus. So that shows the magnitude in one hand, of the storm. The storms are big now these days, and also the size of our countries that are very small. And here's Guatemala, my country. So small compared to India, 17 million people and 108,000 square kilometers. That means that we are 30 times smaller in size. But it's a very shaky place because we are among 3 geological plates. You could see here the North American plate, the Caribbean plate, the Cocos plate. That means lots of quakes and earthquakes and lots of volcanoes, almost 40 volcanoes in that territory. At least 3 of them are active. So greetings to all from the beautiful Guatemala City, the capital of my country, Guatemala. Here we'll see a small introduction and background on the subject that we are talking about today. In the year 2020, everything was okay. Everything was going well. Everything in January, February of this year was good. But then, you know, disaster struck us everywhere. And here's a map on how the cumulative cases look like around the world these days. US, Europe, South America, Central America, Asia, India in particular. You know, almost 60 million cases around the world, 1.5 million deaths globally. That's a lot. In my country, in Guatemala, the numbers you see are small numbers, maybe for everybody, only around 110,000 cases, nearly 4,000 deaths. Fortunately, 100,000 people have recovered from the pandemic, but in a small country as Guatemala, those numbers are large. And here we could see the daily cases and the daily deaths in Guatemala. You could see here the peak of the cases and the deaths were in July, mid-July of this year, around almost 1,500 cases and a little over 40 deaths a day. That's on July. And you could say how has been diminishing. But yeah, looks like we are not even in the second wave yet. So here it looks only down, but we are expecting a second wave, as everybody. So we'll see what happens. So this has terrible effects on every country in the world. The first reactions on March and April were lockdowns and curfews, and that's how our cities and towns look like over here. I suppose that's how it looked in every place in the world. You know, empty streets, empty buildings. That's how it looked here in March and April of this year. And the ready-mix industry, what were the first reactions? It was a shock. What could we do? No more construction projects, everything stopped. And what we start to do as an industry? And after the shock, we thought helping with cleaning the streets with lots of water and soap was the solution and was a great idea, maybe. So we didn't know at the time if that could help with something. Maybe, I suppose, at least was a psychological help, but unfortunately, not more than that. And for sure, nothing that will help our industry in the financial numbers. But at the time, we have the trucks, we have the people, so we try to help. And you could see our budget and our sales, how it looked like through the year 2020. As I said before, it seemed like a great year. You know, here in January and February, we were over the sales budget, 111, 110%. So it looked great. But with the pandemic, you could see the numbers here, the worst months from March to July, being April, the worst of all the months here in sales on ready-mix concrete. Then from August up to date, everything seems to be rather normal, but the damage has been done already. So we estimate we'll close around 85% of the original budget. Maybe not as bad as we estimate on April, because we thought in April that maybe getting to 50% was a good number, but we are getting around 85%, not as bad. But the pandemic has hit us hard, as everybody. Interestingly enough, the cement industry seems to be recovering to the original estimation. The cement industry is getting around 100% of the budget. Could you imagine that? Well, let me tell you that our market here in Guatemala is a strong cement in bags market. We sell a lot of cement by the bag. So maybe that explains the recovery of the cement sales. Or in fact, maybe the cement never stopped to be sold during the pandemic. I think that's what happened. The small market continued to construct here in our cities and towns. But we have to take action. And the projects open again as early as May 2020, taking the proper precautions. Temperature measurements 3 or 4 times a day, a responsibility signature from every worker, health surveys daily, hand and shoe soles washing every hour or so. Even on the helmets, you could find valuable information, even using different colors, ID codes, week number, working area, working sub-area, type of activity, that kind of things. And let me tell you, our construction industry in Guatemala, including ready-mix industry, is very conservative and rather slow, so to speak, where the decisions on the way to improve with new methods and new initiatives could take months, years, maybe. So we have to find new ways to work because we were trying to rescue the year 2020. And we did. is starting with the easy things to do, the cost reductions. We'll see some examples here. For example, starting with the compressive strength. We sell the majority of our concretes by compressive strengths, and it's one of the most important parameters that we measure in plants and projects. In our case, we sell by minimum strength. You know, we could see here a normal distribution of strength results, and to achieve that minimum strength, we have to be able to achieve a mean of required strength, where the results are gathered. We need that to achieve the minimum strength. We have to give more strength as a mean. But the problem is that we give in the range of what I call the gift zone. So that's magnificent for the client, of course, but not much for us, unless in the present circumstances. So we review those gift zones for the different types of concretes and try to reduce them to where they should be, covering the required strengths, yes, but not very much more. And we save tons of cement, and tons of cement are tons of money, So the other important source of cost reduction focuses on achieving synergies between components of the mixes. For example, the proper combination of different types of cement. We have several types of cement with different percentages of supplementary cementitious materials. In our case, it's natural pozzolan. Since we have lots of volcanic ash, that makes sense. Usually, the more SEMs that the cement has, the cheaper it is. Interestingly enough, we found out that we can achieve significantly cost savings when we use a combination of more than one type of cement in our mixes, combining performance with price. So we have to make trials on this, but it pays off, as well as with other components, such as the type of admixtures. The perfect combination could get you huge savings. At the end, these initiatives, such as monitor required strengths, synergy between components, such as the ones I tell you, combining different types of cement or admixtures, could help you to reduce costs. You have to invest in several trials, as I said, but they pay off, believe me. Until now, we have not speak of any technological advance or technical acceleration. But as I said before, our ready-mix industry in Guatemala is very conservative. We usually are not eager to try something new. And meaning by new, I mean new in our market, because probably something old or probably state of the practice in other places, but but not with us. They are not new for us. And probably we know about that new technology, but simply think that, nah, it's cool. It maybe solve some of our problems, but it's not for us, at least not now. And probably we even make some tests or trials with the technology, but no, until something huge like the COVID-19 pandemic occurs, then some of the technology that we thought advanced for us makes some sense, because we either reduce costs or continue operation maintaining social distancing. One of them, in our case, is the rheological control devices that goes into trucks as new components to check on hydraulic pressure, temperature, drum speed, flow valves, slump display for the driver, water and admixtures nozzles, and several features that measure and control slump on trucks, control mixing and automatic dosage of admixtures. For us, that was new. We knew about it, but we don't care to implement it until now. All of these features have direct influence on acceptance requirements on the project, proper workability, maintaining water-cement ratio and strength, reducing the coefficient of variation. That was very important, to reduce the coefficient of variation, because that permits to reduce the amount of cement in the mix and make it more economical. And optimizing mix design. The direct benefits on this are that you have more homogeneous concrete with no rejections, which means zero disputes with the clients on site, a task that consumes so much time and money. Also concrete stability and slump control. The mixing time is optimized also. The plant and in project dead time per truck is greatly reduced. So you don't have the trucks too much time waiting or losing money. All this mean money, $2.5 to $5 per cubic meter in savings. That's what these devices could save for you. And that's a lot of money. The other initiative is an example of what we are doing, is estimating the strength of concrete by its maturity. In Guatemala, we measure strength by making specimens on site and then test them on the lab. But as you see, making and handling specimens on site can influence directly in poor strength results that are not in accordance to the placed concrete. By establishing a relationship, a correlation between strength and temperature of the concrete, you can finally estimate on real time, and that's the important phrase, real time, the strength of concrete in the element or structure. Here you could see some trials on this technology that we are implementing. Those are sensors and sensor cables, the reading device that helped us to validate this technology. And among the benefits we have, prediction of the actual in-place strength of concrete is important, and the phrase in place is very important because you don't have that with specimens. Consistency on results. The results are collected in real time, another important phrase with this technology, real time, and the promotion of social distancing. And that is a direct consequence of the pandemic, because really, we didn't care about that before. Are you kidding? We love social gatherings. We love social events. We are Latin Americans. We love that. We love to be close to each other. But we understand now we have to take care of this. And this methodology will help us maintain our distances. Also, we have direct cost savings compared with on-site quality and lab teams, instead of having people on the job site. Accurate job site planning, so knowing when to remove forms, for example, and financial savings as a whole for early completion of projects. So that means also a lot of money. We are still determining the amount of the savings we'll have with this initiative. We are working on it. And finally, as conclusions of this presentation, we know COVID-19 caused very negative impacts on the construction industry and the ready-mix industry, that's for sure. But with proper actions, we were able to come back. Probably not to 100%, but we are doing better than we expected in April of this year. And also, COVID-19 was an accelerator. You know, it seems like contradictory, but something bad accelerates our technology for new ways of doing things that maybe before we were afraid to use, you know, but now we use it thanks to COVID-19. So then, thank you very much for your attention, and hope everyone is doing well wherever you are. Thanks. Thank you very much. Good day.
Hello and a very warm welcome. Myself, Martin Scheurer, and my colleague Shantanu Bhatt will present to you Textile Reinforced Precast Technologies, an Indo-German collaboration for reviving the construction industry. Today's presentation is separated into 4 parts. First, I will introduce the Institute for Textiltechnik of RWTH Aachen University and the Department of Construction Composites at ITA. Afterwards, my colleague Shantanu Bhatt will showcase ITA's collaborative activities with India and how to revive the construction industry using textile reinforced precast technologies. The Institute for Textiltechnik Aachen has a staff of about 100 scientists working in all areas of textile development, textile production, and textile application. In addition, we boast about 60 technical and service staff, 190 undergraduate research assistants, and about 50 students who major in textile engineering every year. The expertise of the ITA reaches across the whole textile production chain, starting with fiber production, continuing with yarn and fabric production, and reaching into composite and semi-finished part production. This large area of expertise allows for a multi-scale formability across all process stages, where the needs of the semi-finished parts can be incorporated even into the fiber production, and products and developments can be tailor-made for each and every application. The ITA focuses on 8 research domains as shown on this slide. These are building and living. Part of this research domain is, of course, the Department of Construction Composites, as well as the research domains of energy and environment, mobility, production, information and communication, health, materials development, and qualifications. The Department of Construction Composites at ITA focuses mainly on the area of building and living. The department consists of 5 researchers as shown in this picture. One of the main topics of the Department of Construction Composites is TRC, or Textile Reinforced Concrete. The basics of this new material are showcased in this slide. Textile Reinforced Concrete is a composite material consisting of 2 parts. The first part is the fine concrete, which is with a fine concrete matrix of aggregate sizes of up to 5 mm with adjusted flow properties offering a very high surface quality. This concrete is then reinforced using a textile reinforcement, which replaces the traditional steel reinforcement. The textile reinforcements are made of carbon or alkaline resistant glass rovings with teters up to 3,600 tecs. These textiles are usually fashioned into a biaxial warp knitted fabric or a 3D warp knitted fabric, and both parts of the composite are placed together, resulting in TRC. TRC composites are corrosion free since the reinforcement does not corrode, dissimilar to traditional steel reinforcement. In addition, TRC composites are structurally strong because especially carbon fibers, offer very high strength. They offer a high design freedom and a negligible concrete cover. So textile reinforced concrete offers many advantages over traditional steel reinforced concrete. The reinforcing materials are usually carbon and alkaline resistant glass, as mentioned before, but in addition basalt fibers and polymer fibers, for example aramide, PVA or PP fibers, can be used. Here, the reinforcing materials can be tailored to each application. For example, if very high strength is needed, carbon is the material of choice, but of course carbon fibers are quite expensive, so if less strength is suitable, it's better to use alkaline resistant glass or basalt fibers. Why should you use textile reinforced concrete? In steel reinforced concrete, the concrete bears compressive forces and the steel bears tensile forces. This combination of material properties has led to the high success of steel reinforced concrete, making it the most important building material globally. However, the reinforcement is corrosion prone and requires a thick concrete cover, leading to high weight of the materials. Of course, Steel reinforced concrete also offers a wealth of experience with more than 100 years of the material being in use and many general building approvals being available. However, the transition to textile reinforced concretes offers resource savings of up to 80%, leading to reduced CO2 emissions of up to 80%. Thicknesses can be reduced, depending of course on loads, by up to 70%, and the weight of building materials or precast elements can be reduced by up to 50%. In textile reinforced concrete, the principle remains the same. The concrete bears compressive forces and textile bear tensile forces. However, the reinforcement is not corrosion prone, leading to thin concrete covers, less weight. Still, the material is relatively new, with first experiences being made about 20 years ago and no general building approvals being available yet. Here at ITA, we do not only focus on TRC, but also on other composite materials. Especially, of course, as a textile institute, we focus on the textiles for reinforcing, for example, in TRC. These are biaxial warp knitted fabrics, which we can produce here at our institutes. In addition, we focus on intelligent textiles and product by functional integration, by means of using technical textiles. And these technical textiles can offer a wealth of additional functions, for example, surface heating, sun protection, heat protection, etc. In addition, we also study 4D textiles, which are facade textiles that can adapt to environmental influences over time by textile integrated mechanisms. For example, closing a sunshade if the sun is high in the sky. In addition, we've researched shaped fibers for acoustic insulation, for example, used in office spaces or in event locations. Another focus of our institute is sustainability. Here we develop new sustainable resource-efficient materials, such as TRC. One very important topic for TRC is the design for recycling of textile reinforced concrete, where we already plan now for reuse of buildings built with TRC after their lifespan of up to 80 years is exceeded. In addition, we research the application of recycled short carbon fibers in concrete and mortars, and we do efficiency analysis of composite production processes to decrease material and cut-off waste. Another area of research is in geotextiles, where we do machinery development for production of linowoven fabrics with high grid sizes as suited for geotextile applications, and we work on integration of warning systems in building and dikes to prevent natural disasters by using smart textiles and integration of sensors. By integration of sensor fibers, for example polymer optical fibers, carbon fibers, or other sensor fibers during the textile production, so that the sensor is integrated directly into the geotextile, and the geotextile can be used for reinforcement and sensing simultaneously. All these developments we do at our institutes are not only theoretical in nature, but we have also produced a lot of demonstrators over the years. For example, in 2009, while just building our new machinery hall, we built halls with the first TRC sandwich facade worldwide, and the facade still looks as good today as it looked the day it was built. In addition, we developed light-transmitting concrete facades in cooperation with the industry, functionally integrated TRC roofs, which integrate either photovoltaics or thermics into the roof elements, and we developed curved concrete elements, as showcased in the pictures on the right, which show that textile reinforced concrete offers highly adaptable thin structures with thin-walled elements for architectural purposes and to reduce weight and improve resource efficiency. We offer here at ITA a cooperation along the entire value chain, starting with the textile development and with 2D and 3D warp knitted reinforcement textiles, as well as lino weaved textiles. Continuing with textile finishing, where we do coating of textiles on lab and pilot scale, and the sensor fiber integration if necessary. We also allow for prototyping in our concrete lab, where we manufacture prototypes as well as standard testing specimens, and we also have a polymer infusion labs analyzing polymer coating materials. And we have an acclimatized testing facilities where we can do fiber, textile, and composite testing, as well as optical and electron microscope tests, as well as an X-ray CT.
Thank you very much, Martin. Hello everyone, I'm Shantanu Bhatt from Construction Composites Department at ITA. Over the next couple of slides, I would like to share with you ITA's collaborative activities with India over the past couple of years, and also how we can together revive the construction industry using textile reinforced precast technologies. Our institute has been working in close collaboration with different universities and industry partners in India. In 2019, the Indo-German Science and Technology Center Governing Board meeting was held here in Aachen, Germany. The main purpose of the meeting was project initiation of 2 Indo-German projects granted to ITA and IIT Madras along with their industry partners from Germany and India. Delegates and technical experts from IIT Madras and IGSTC visited ITA to discuss and devise a plan for the execution of the 2 projects, Clean Water and NearNet-MAC, which will run until 2022. The meeting was also attended by Consul General Ms. Pratibha Parker of the Indian Embassy in Frankfurt and Professor Thomas Gries, Director of ITA from the RWTH. In the impressions on the slide, we can see my colleague from ITA showing the board members and the delegates the facilities at ITA for the development of textile-based solutions. Moving ahead, at the 3rd Indo-German Symposium, topics and opportunities for innovation and entrepreneurship in Germany and India were discussed. The focus was on startups and cross-border opportunities to channelize the developments made in the textile field at ITA into the Indian market through campaigns like Make in India and other government initiatives. Now I would like to throw some light on one of the 2 projects which were initiated at the IGSTC board meeting, which I have mentioned before. The project name is Clean Water, and the goal is development of modular lightweight wastewater treatment units made with TRC for rural and peri-urban dwellings. The project was initiated to tackle problems of untreated wastewater which is being discharged into the environment. Many regions have no access to wastewater treatment plants, and also the high energy and space requirements which the current systems need. Hence, the aim was to develop, manufacture, and implement a modular, low maintenance, energy saving, textile reinforced concrete wastewater treatment plant. Using textile reinforced concrete, the sewage plants can be made modular and of low maintenance. And the approach adopted for this project was to first of all develop a design for TRC wastewater treatment plant. Secondly, to verify the load bearing capacity and suitability for use of the sewage plant at the respective site. And at last, to develop a transport system so that this wastewater treatment plant could be set up even in the most secluded villages in India. We at the Construction Composites Department at ITA are glad to have carried out projects with countries like Canada from America, Korea, Japan, and India from Asia, amongst others. And this has helped us develop a widespread international network which keeps us up to date regarding the recent advancements in the field of textile reinforced concrete. For some of our target countries, we also have dedicated country representatives which cater for the hassle-free coordination of the project activities. Now I would like to come to the last part of our presentation and share with you the views of our department and how we think we can revive the construction industry using textile reinforced precast technologies and be prepared in future for unprecedented calamities or more specifically pandemics like COVID-19. Now I would like to put forward two research topics which we think will be beneficial for the revival of the construction industry. Firstly, textile reinforced 3D concrete printing. 3D printing has already found its way into the construction industry. There are already houses being 3D printed, but the deficit at the moment is that the 3D printed concrete doesn't have any reinforcement, and hence the absorption of the tensile forces is only possible via the matrix, which in most cases is not that strong enough to sustain the forces which act upon the building. And thus, the aim is the realization of endless fiber reinforced 3D concrete printing process. The approach which can be adapted for 3D printing of endless fiber concrete is with the help of robots and textiles, and hence we aim at development of a process for the production of 3D textile reinforced structures. Another way in which we can revive the construction industry is by using the adaptive molding technology for the manufacturing of doubly curved textile reinforced facade elements. Often is the case that when we go for freeform architectural buildings with complex shapes, as the one shown in the top right corner of the slide, the mold costs for such a building are 35 to 60% of the total production costs, as for each element of the facade a different mold needs to be fabricated, which makes the whole molding process very cost intensive. And also, if we don't use textile reinforced concrete, then the facades also become very thick, which then limits the freedom of design of these facades. Hence, the aim here is the realization of non-repetitive, doubly curved, thin-walled TRC facade elements with the same adaptive mold. Here with the adaptive molding technology, a set of pins take different shapes when they move vertically with the same mold, and hence it is possible to fabricate both repetitive as well as non-repetitive facade elements with the same mold. And the approach which is to be adopted here is, first of all, to develop a drapable textile reinforcement for thin complex shaped facades. Here a multi-axial textile grid structure which is drapable will be developed, and then this developed textile will be used with the adaptive mold for manufacturing of thin walled facades. Apart from that, a suitable concreting process for fabricating TRC facades over the adaptive molds also needs to be developed. Now I would like to go through the ways in which we can work together on the topics which we find interesting, and also of course on the topics which you think could be of interest for both of us. We can work together via public projects which are financially supported by the respective governments, and the funding instruments through student and scientist exchange programs and trainings. Also, uh, we can work together with the sister concern of our institute, the ITA GmbH, in form of R&D projects which cater to the industry company industry and company specific needs. framework contracts such as MOUs between universities, innovation workshops, literature and patent research, student theses, training courses. These are exclusive to the needs of our partners, and there is also arrangement of confidentiality so that whatever is being developed is not publicly available. Now I would like to summarize our today's presentation in a nutshell. ITA is leading textile research institutes in Europe with more than 20 years of experience in textile reinforced concrete. The first tests on textile reinforced concrete were done at our institute back in 1998. TRC offers multiple advantages over steel reinforced concrete like higher strength, less weight, eco-friendly, and resource efficiency, which makes TRC suitable for precast elements. And thus TRC enables a sustainable revitalization of the construction industry as due to the lightweight, transport costs are being saved. Due to the material efficiency, less cement is being used. We are constantly looking for research partners with whom we can collaborate and further develop the textile reinforced concrete technology. With that being said, I have come to the end of my presentation. We will be pleased to discuss further with you in detail about the different collaborative opportunities. Please feel free to contact us. Thank you from my side and also on behalf of my colleague Martin Scheurer for your attention. Stay safe.
Good day, everybody. This is Genaro Salinas. I am talking, and I'm going to show my location. This is the North American continent, and these are the two countries get together, United States of America and Mexico. Between these two countries, we have a border area that is being growing because of the commercial treaties between these two countries. And you will find on this location cities that share friends, family, and partners. The last 50 years, this trade between these two countries has been increasing, and there is a lot of work on light industry. It started at the Chihuahua State with the main cities on the north, Ciudad Juarez, with about 1.25 million people, and some more important cities on the Chihuahua State. The growing of this area on commerce and trade has been so great that we are working on light industry. This light industry is on auto parts, electronics, medical supplies, home appliance. This is the type of buildings that we have for this purpose. And we have, on this period of time, changed some of the things on these buildings, like the roof moves from laminated asbestos to a standing seam steel. The walls from masonry concrete units to tilt-up concrete tilt-up panels. The volume of these buildings increases from the distance between floor and ceiling from 6 to 12 meters. And the industrial floor slabs, we have changed it from a strength of 20 to 35 megapascals and distance in joints from 4 to 30 meters. And this is the kind of large floor slab that we are building right now. On this time, because of the pandemic that we are having right now, this is the way we are doing any signing on the outside. Right here on the top right, all the signals that we have inside and outside of the building. On your left up, you will find some sanitation areas where you can clean yourself and be protected. And inside you have a different type of signs talking about the equipment needed on different areas. Lower right, you will find checkpoints at the beginning of the construction where people is being checked by temperature and other health issues. On your left bottom, you will find people taking some courses about safety, the equipment that had to be used, the safe distance to work. On the upper right, you will find the cleaning of the different areas where we clean also the machinery and tools and desk and all over the area. On your left up, you will see people working on the lab with all the equipment required. The goggles, cover, mask, gloves, and all the safety equipment. Since the beginning of the production of concrete, everybody is keeping the safe distance and all the protective gear. Even in the lab and on the construction, like on these big floors that are from 1,000 to 2,000 square meters daily. Even at different hours of the day, the inspection always keep their safety gear. And all operations during the construction, everybody has to wear the safe equipment to the end. Because of this big boom on this industry, a lot of people came from other parts of the country, and we have an unemployment rate of 0. So we need to have housing for this population. And right now we're working on this housing on a precast mode, like right here. Before that, it used to be this way with handmade clay brick post and beam construction. This type of construction that we're using right now from precast is what we use right here. This IMSS means the government department that deals with social security services and health services. And this is a hospital, a 60-bed hospital that we built it in 15 days with the same precast mode. All the equipment but set and ready for any emergency on the pandemic. This is the team that design and inspect the construction of this hospital right there. And here are all the people that did the work in a safe mode as I'm talking to you. Well, this is it. Have a good day. Thank you very much.
Friends, post-pandemic
recovery is very important aspect for survival of human race.
and unless we are prepared for the same in advance, the challenge or challenges are going to be multiplied to cope up. Innovations and their integration in the mainstream practice of concrete technology is going to be the key to success. So the subject chose our discussion in our regime of post-pandemic recovery is need of smart materials in concrete technology. This is an imperative. As all of you know, post-pandemic recovery of construction industry in general and concrete industry in particular is going to be an uphill task. We have been experiencing it for last almost 10 months. Three aims, I call them: manpower shortage, material shortage, and money shortage are going to be the main hurdles in staging the recovery in short run as well as long run. And that's why, friends, innovation and incorporation of smart materials only can overcome these hurdles. It can happen for greenfield projects as well as brownfield projects because both require 3 M's. What we have to look at? We have to look at that in time to come, we have to reduce person-to-person interface. That is social distancing, respecting social distancing. This means despite low availability of manpower, still we have to enhance the output, the production. Then this is about manpower, social distancing. Then we have to optimize the use of construction materials. We have shortage of materials, so we have to optimize that. At the same time, we have to make sure that the durability of the structure is also enhanced. And this together will in turn give rise to lower carbon footprint and reduced expenditure, at the same time overall leading to sustainability. This smart concrete concept is there since last few decades, 2 decades, but it has not become popular yet. That is why. Why? Because probably the need was not felt, which is so much now today. So in smart concretes, self-cleansing, self-sensing, self-adjusting, and self-healing types are prominent concretes, and they are, like I mentioned earlier, they are useful in green as well as brownfield constructions. Today's presentation, we will deal with, of all these inputs, of smart inputs, we will deal with 4 smart items amongst many, and they will be self-healing concrete. Self-healing concrete will avoid cracks in concrete and enhance the structural stability, at the same time durability. Then we will talk about gaining the strength of concrete without external curing, which involves lots of manpower, and again there are possibilities of error, human errors. Third point will be enhancement of service life. Corrosion. Due to corrosion, lots of damages are happening, and we will try to mitigate with smart materials this corrosion and enhance the service life. And the fourth point is very important in post-pandemic era, that we have to maintain the clean environment. We have to reduce the air pollution, and that is by reducing the pollution effects on the structures. For that, we need to identify origin of air pollutants, we have to identify effects of pollutants, and then ultimately use of photocatalytic materials to clean the environments and make the environments cleaner for us to inhale or exhale. We always see that most structures do not even give effective service for 25% of their service life also, and that is mainly because of the cracks. When the cracks appear, then the corrosion takes place, and when the corrosion takes place, repairs and re-repairs exercise begins, and that is where we can use two smart technologies. One is self-healing microbials, and another one is dispersion of nanopolymers in fresh concrete. When microbials are considered, the known microbials are Cornhill, Phyla, Pasteurella, Subtilis, Sphaericus, calcium lactate, and these come together to form this calcium carbonate in the cracks, in the crack volume, and crack gets smartly, automatically bridged up. And what is the smart thing? Another smart thing about it, that this becomes active only and only when the cracks are developed and the space is created to get filled. And this will not require any labor. This will not require new money, or this will not require any material, because all these three M's have been utilized right in the beginning of concreting. This is the pathology of self-healing concrete cracks. In first top diagram, you can see the crack developed. In second diagram, you can see these microbials and sodium lactate, they are coming in contact with each other to form calcium carbonate. And this yellow material, what you see, is calcium carbonate, which is formed in situ, and the crack has been filled, thus allaying the fear of danger or corrosion to the concrete structure. I talked about second option, nanopolymers. Nanopolymers are nanoparticles of liquid monomer, and that liquid monomer is easily dispersed throughout the concrete, and being nano in size, though used in very small quantities, it is present everywhere throughout the concrete. Now, whenever the crack develops, like we are seeing in this picture here in the first picture, the crack has started to develop, and second picture, the crack has developed more. Whenever the crack has developed more, and whenever the crack has appeared, the nano tubes or nano encapsulated monomer tube, they will get accumulated in this crack. They will get the encapsulation will break, and then that monomer will convert into polymer, filling into entire empty space, resulting into no loss of structural strength, concrete strength, or no ingress of moisture or chlorides from outside. Second point we want to talk about is curing. Unless curing is done, curing is an unavoidable operation. Unless curing is done very, very diligently and for a given number of days, the concrete structure suffers in its service life, suffers in its strength, suffers in the cracking pattern. So gaining the strength without involvement of human being, without involving any external operations, then it will be a smart thing, and we are going to talk about the same. These are the classical methods, good methods, classical methods. Classical methods of curing. So there are fogging, wet covering, membrane forming compounds, then impervious paper and plastic sheet. All these are good, but they are man dependent, human error dependent, and time dependent. If there is any mistake in any of these, then the curing suffers, and in turn the structure suffers. Now in post-pandemic, all these mistakes are unaffordable because we have shortage of manpower while doing the green structure itself. Then we have shortage of funding, shortage of resources, and also we are having shortage of materials. So the large structures or small structure, both the places, the curing has to be taken place somehow continuously, and that can happen only with a smart way. What we do is this: what you see in first two slides over here is the concrete external curing. What happens is really water just penetrates inside and keeps the hydrated concrete in the hydrated form, and reduces the escape of hydration water from the concrete to outside. But again, it is subject to the errors that I mentioned earlier. Then in this we can see that whenever we are using internal concrete admixture, like I am showing over here underneath the classical this curing, what will happen in post-pandemic? If you try to do classical curing like water curing over here, then obviously because of shortage of manpower and other things, the curing will not happen, and the depth of concrete curing also will be much less, as you can see here. However, if it is mixed throughout the concrete, the polymers, internal curing polymer, then it will get dispersed throughout the concrete. This polymer will have a special absorption of water capacity, and that polymer, when dispersed throughout the concrete, will go on releasing water for hydration, and the concrete hydration will be more towards perfection. Workmanship, scarcity of water, lack of awareness, need of conservation of water, all these points are very important in post-pandemic days. However, this table here is self-explanatory, that in trial 1 we have not used any water curing compound, any water curing. Trial 2 we have used this without admixture but water curing. Trial 3 we have used water curing, internal curing admixture, but without water curing externally. And trial 4 we have done water curing as well as internal admixture, and the compression strength results are speaking for themselves. Today, in desert areas and all such conditions where water shortage is there, these materials are very effectively used and giving good results. However, post-pandemic, this should become a habit of construction industry. We are going to talk about now corrosion mitigation. Corrosion mitigation can be done by giving coatings to the steel, by giving coatings to the concrete, but then there are always chances of errors, and because of that, the performance of corrosion prevention suffers. And corrosion, as you know, is a continuous process. It never sleeps. I mean, there is a small entry to these enemies of steel, that is moisture or chloride or SOXs, NOXs, then in that case, erosion will start. So what we need to do is we should have, which erosion losses are huge, as you can see over here. Erosion losses in India itself are to the tune of this astronomical figure per annum. So you can imagine what must be the cumulative losses in a large country like India, and you can extrapolate how much must be the losses for anywhere else in the world for that matter. This is a damage versus time versus cost graph. Now this damage and cost are on y-axis and time is on x-axis. Ideally, we would like building or a structure to have damage going to parallel to x-axis, but then because of the external condition, the damage enhances, increases, and then we have to intervene, that is repair 1, say repair 2, say repair 3, and repair 4. So in post-pandemic era, if we just look at this cycle of repairs and ultimately approaching the end of serviceability, then we are talking about additional cost of manpower, additional cost of material, and additional cost of money. So these three are unaffordable 3 M's, and that's why it's very important to avoid corrosion at all costs, if possible, smartly. We are using in green concrete chemical materials called ligands, and these ligands, they form a stable compound with the interaction with metal. So this metal in this case is steel, and they form around the steel monomolecular layer without any blemishes, without any fall, and that is what is protecting the steel for many, many years to come in the service life of a structure. The mechanism will be something like this, that these molecules are spread all over the concrete, and I'll show it to you once again, and they will be attracted towards steel, and they will be forming this without any pinholes, without any false defects, the coating around the steel, which will not allow steel to corrode anymore. Obviously, these are useful for structures either in the greenfield zone or brownfield zone all throughout the life of the remaining service life. Now, we talked about clean environments and reduction in air pollution. Now, this can be done, I mean, as we see many structures, or all the majority of the structures, unless they are repeatedly painted, they are turning blotchy, or there are spots on them, or there are big clouds of these algae formation also are on them. So that is all happening because of air pollution and its growth on the surface. So we need to identify origin of air pollutants, effects of pollutants, and then photocatalytic material, that's the remedy, photocatalytic material to clean the environment. Photocatalytic materials means catalytic degradation of these impurities happens with the photoenergy. Photoenergy comes from nowhere else but the solar light. These are the pictures of pollution in various metros of India. So the case is same everywhere, and this is mainly because of the growth of motor vehicles. We are having about 30 million motor vehicles in the country, and they are growing every year by a large number. These vehicles emit carbon monoxide, NOx, nitrogen oxides, then volatile organic compounds, and this also offers great danger to human respiratory system as well as the environment. These are the other effects of this pollution: acid rain, and mild algae growth, ozone layer impacts. So what we are looking at now, these are the structures, how they look like, and we don't want them to look like this. We want them to look fresh every day, every month, every year, year on year. So what we do is we do some sort of brainstorming, and in brainstorming, the question comes: how? By reducing number of vehicles? No. By converting all those 30 million plus motor vehicles in India alone to this compressed natural gas, CNG, I don't think it is possible. Then are we in a hopeless situation? That means because of this smart material, we are not. And these smart materials, photocatalytic materials, to be used in concrete itself, they will protect the cities and the rural area on day-to-day basis throughout their lifespan of the structure, and this will happen whenever sun is shining. That is almost every day, barring few days in rainy season, and that is smart. Photocatalytic material, like I mentioned earlier, is mixed in the concrete, and when it is mixed in the concrete, pollutants are oxidized and decomposed in the presence of photons, photo light, and the action is antiseptical also, because it deals with the destruction of these algae, and that's why it is antiseptical, and it self cleans. It keeps the surface clean, and these are the replenishable materials, and that is why this becomes very smart case. Here are some examples just for your reference, that in Antwerp some years ago, a large area of parking lanes was treated with this, and there was a substantial difference in the levels of these polluting gases was found, and there are photocatalytic pavement blocks they made. Similarly, in Netherlands also it was done successfully, and now it is happening at quite some places. So after this, we have to look at other options also. Other options in smart solutions could be sleeping concrete, could be zero energy concrete, could be progressive time-based soil stabilization, bendable concrete, conducting concrete, which is very important for new smart cities and monitoring vehicular traffic. These are some possibilities of smart construction of materials, but let's begin at the basic four so that we can save on our 3 M's: manpower, material, and money in post-pandemic area. So in conclusion, self-healing concrete, internal curing, smart construction, mitigation and photocatalytic chemical cleaning of environment can be smart solutions to overcome the 3 M's: manpower again, material shortage again, and money shortage again. Thank you for your attention.
Many of the engineers today do believe that ultra-high performance concrete is developed by Lafarge in the early 1990s. Hans-Hendrik Bagge, working as a research engineer for the cement and concrete laboratory at Aalborg, Portland, Denmark, was working on high-strength concrete since 1964. Bagge believed that cement particles should be packed much more densely, corresponding to a water-cement ratio of about 0.20. Based on Griffith's classic theory for the tensile strength of brittle materials with a single sharp crack, Bagge believed that the method to reduce the porosity was the use of very fine cement. But at that time, early 1970s, cement particles, and especially very fine cement particles, could not be dispersed in a small amount of mixing water due to surface forces. After the development of superplasticizers in Japan and Germany, a much denser packing of the cement particles became possible, and this resulted in a much lower water-cement ratio between 0.32 and 0.38. Since it was in 1978 possible to disperse very fine cement, Bagge experimented again with a blend of cement to reduce the pore size between the cement particles. After contact with a Norwegian colleague, Bagge started to use microsilica and reached the ultra-high strength of 280 megapascal in his first samples. The use of the very fine spherical microsilica to fill the spaces between the densely packed angular cement particles resulted in a very low water binding ratio of 0.13 till 0.25. This technology has been patented, what is explaining that later developments started after the 1990s. In 1986, Hans-Hendrik Bagge developed compact reinforced composite, a UHPC with a water binding ratio of 0.13 until 0.18, and reinforced with 5 until 10% steel fibers and combined with 5 until 20% main reinforcement. Compressive strength 150 until 400 megapascal. Flexural strength 100 until 350 megapascal. Shear strength 15 until 150 megapascal. The structure of these new composites is built of a very strong cementitious matrix, which is being provided with toughness through incorporation of fine fibers and a very high concentration of reinforcing steel bars. Compact reinforced composite has a superficial similarity to reinforced concrete. It has, however, a much higher load capacity, not only in compression but also in tension. Since 1978, the UHPC as developed by Bagge has been tested, investigated and described in publications and proceedings. Often it was classified as ultra-high strength concrete. Shortly after, many names, mostly related to the compressor strength and not to the performance, are used to differentiate UHPC materials from traditional concrete. In 1983, Aalborg Portland founded Densit AS. Densit AS created 4 separate divisions to develop and market the UHPC in the business areas. Security industry. UHPC is used as a barrier material in vaults, strong rooms, ATMs and protective structures against explosives and other threats. Wear protection. UHPC is used as wear lining in systems with abrasive wear, like in cement factories, coal-fired power plants, steel factories, etc. Very hard, wear-resistant aggregates like silicon carbide, corundum and calcined bauxite are used while the material can be applied by casting, spraying, hand trolling and prefab made elements. The UHPC can replace many other materials and is used, for example, to replace the cast iron scope feeder in cement factories, resulting in a much longer service life. Civil engineering. UHPC is used as shotcrete to be applied in very thin layers, abrasion erosion resistant overlays and toppings in sluices and dams. UHPC is used as semi-flexible pavements, toppings and overlays on industrial floors and pavements and bridges. UHPC is used as a repair material for corroded piles and later as a structural grout for the strengthening of offshore platforms and offshore wind farm foundations. Compared to a traditional concrete, a traditional UHPC contains 50 to 100% more cement, and we know that the cement industry is one of the main producers of carbon dioxide, a potent greenhouse gas. By using supplementary cementitious materials as a replacement of cement, a more sustainable UHPC can be produced. An example of using supplementary cementitious materials as a replacement of cement are the in 2018 developed extreme UHPC materials. The Cement and Concrete Laboratory of Aalborg Portland in Denmark is taking again a leading role in new developments. White cement is combined with white metakaolin, limestone and additives, resulting in a very white UHPC with a very low autogeneous shrinkage. More and more produced UHPCs are using a design philosophy based on sustainable construction, taking the possible and or potential impact on our environment in account. This is complex, since all parameters should be taken in account to get a reliable output and comparison with other construction materials. A UHPC technology design philosophy is a limit state design and durability design that is taking sustainability construction into account for an optimum balance between total service life and UHPC performance. Consist of performance needed for an UHPC. By using an environmental-based optimization, the correct choices can be made for sustainable construction by material optimization, in which the selection of materials, the possible use of recycled materials, and using supplementary cementitious materials are priority for the production of UHPC. By optimizing the shape, the structural design and service life of elements and whole structure, formwork, storage, handling, transport, and handling on site can minimize waste of materials, transport and handling, and reduce the impact on our environment. The material design and properties of the UHPC are important for the total service life, with the minimum of maintenance and repair. However, to design a structure for 200 years, while the service life will be 50 to 100 years, is only making sense when the structure can be completely or in parts reused. Potential reuse of structures and or recycling after a long service life is an interesting option and needs to be investigated. Since 1978, Hans Hendrik Bagge made different designs to optimize the use of UHPC in structures like bridges, resulting in slender structures and large spans. Today, we see that many engineers are trying to put this in practice and to calculate and design bridges with very large spans, up to even 1,000 meters. Dura technology in Malaysia is taking a leading role here, and several hundred slender bridges, often with large spans, are built with UHPC. UHPC is, despite the large amount of cement used per meter cubic, an interesting alternative for traditional concrete and steel, and, when an environmental-based optimization is used, lower impact. Standardization of elements and structures will even result in a much lower impact. Heicon AS in Denmark is the first company who obtained an environmental product declaration for a type of precast balconies. A very detailed investigation has been made to have all data taken into account. The product declaration is based on a life cycle assessment in compliance with the requirements of the European standards. Compared to traditional concrete balconies, the UHPC balconies are having less impact on the environment, with 25% less carbon emission. Fine-tuning of the UHPC can result in larger differences. The use of hybrid reinforced UHPC to strengthen and rehabilitate structures is often an interesting option to save materials, to create less waste, to avoid closure of roads and bridges during a long period, and to extend the service life. Here, the thick wooden beams of a bascule bridge in a main highway are replaced with very slender, hybrid reinforced UHPC panels within the total weight tolerances, but with a much longer total service life. Remarkable is the thin cover of only 50 mm on the reinforcement bars. By using Bagge's compact reinforced composite principles, extreme strong and ductile structures can be created. After loading the test plate with up to 18 tons of concrete blocks, the panel finally collapsed due to fatigue of the reinforcement. Using stronger reinforcement, like high-strength steel, tendons or Kevlar, will result in a much higher flexural strength and fatigue resistance. Very slender hybrid reinforced UHPC panels are used to replace deteriorated existing reinforcement concrete decks on steel bridges. This is reducing the dead weight of the deck and thus total structure, and resulting in a durable deck and an extension of the total surface life. After placing the slabs on the new girders, the connection between the UHPC prefab panels and the new girders with studs are grouted with an UHPC to create a durable connection. Originally developed as CNC joint cast in Denmark by Aalborg Portland in 1994, to join prefab concrete slabs in the middle of a span and over the columns for 2 new buildings at Aalborg University, used to provide a solution that is better, faster or cheaper, and, when possible, all of those. Examples could be where traditional joints are much too complicated or too expensive, or where the possibility of having a full-strength joint in 3 days can be used in the building process. Investigated in 1998 in a project with Swedish Strangbeton to replace traditional used joints in precast bridge slabs. Contractor Shimizu from Japan has carried out several tests on CNC joint cast in 1997. The first of these tests concerned a joint between 2 beam parts. CNC joint cast has been investigated in 2001 in a large research project carried out by Building Research Establishment in the UK. Accelerated bridge construction consists of innovative bridge construction methods that are used in a safe and cost-effective manner to minimize the inconvenience to the traveling public while delivering a superior finished product. This technology has become common over the last 2 decades in the United States, and many states are considering ABC on more typical projects. The use of prefabricated bridge elements facilitates ABC. These elements are typically produced in a controlled environment that facilitates high production quality. The most critical field construction process for prefabricated elements are the connections between the elements. In general, connections must be robust, durable and efficient. One common connection method involves the use of field cast concretes or grouts in the interstitial spaces between the prefabricated components. Worldwide, thousands of concrete bridges are underdimensioned and or deteriorated, and since the late 1980s, UHPC overlays are used to strengthen bridges and to replace the wearing courses and concrete decks. To have a very effective strengthening, CNC principles are used to create hybrid reinforced UHPC overlays, which can be durable bonded and anchored to the structure. Also in the Netherlands, many bridges, especially when built in the 1960s until 1980s, are underdimensioned and often deteriorated due to chlorides. In a small country with many rivers, bridges are essential, and long shutdown periods for repairs and replacing are unacceptable. The hybrid reinforced UHPC is an ideal solution to strengthen and to replace deteriorated concrete decks and to extend the total service life of the structure. In 1999, I designed a solution by using a hybrid reinforced UHPC overlay to strengthen concrete bridges and viaducts, to be able to use the complete width of the viaduct and to allow heavy trucks to use the emergency lane at the shoulder of the viaduct. Often the bonding is not sufficient due to the properties and deterioration of the existing concrete deck. I use the good, the bad and the ugly method to differentiate the quality of the existing concrete deck in the design. In most cases, I do believe that shear anchors are necessary, and I suggested a combined system of a stud with an adjustable plate as a leveling of reinforcement and shear anchor. Application of the UHPC with a slip foam paver is not only very practical, but is also technological the best option. Fast placing, extreme compaction, low shrinkage, very high compressive strength and extreme durability are the result. In Switzerland, many deteriorated bridges are strengthened and rehabilitated during the last decades. UHPC is also replacing the very expensive waterproofing used before to avoid chloride penetration in the concrete structure. Approximately 25% of the 600,000 bridges in the US require rehabilitation, repair or total replacement. However, the work that occurs from on-site construction activities can have significant social impacts to mobility and safety. In many cases, the direct and indirect cost of traffic detours that result from the loss of a bridge during construction can exceed the actual cost of the structure itself. For example, full lane closures in large urban centers or on highways with heavy traffic volumes can have a significant economic impact on commercial and industrial activities in the region. Partial lane closure and other bridge activities that occur alongside traffic can also lead to safety issues. Because of the potential economic and safety impacts, minimizing traffic disruptions is a goal that should be elevated to a higher priority when planning bridge-related construction projects. Royal Flora Holland is world's largest flower auction and world's 5th largest building. A cold store for flowers, a former indoor parking deck, thus designed for relatively light dynamic and static loads, was created by using foam glass insulation panels with the hydraulic bound bitumen emulsion as topping. Relatively fast damage occurred due to the high dynamic loads and static loads of the transport vehicles and flower carts with small hard wheels. The consultant tried a lot of potential solutions, but nothing worked. I made a solution in 1994 without removing and replacing the insulation and topping by placing a 22 to 24 mm hybrid reinforced UHPC topping. By adding welded mesh reinforcement round 6 mesh 50 mm in combination with the ultra-high performance fiber reinforced concrete, a flexural strength of 80 megapascal is possible in a thin 2.5 cm thick layer. The client is very pleased because the floor is still working after 25 years in use. In 1999, I was invited to write an article about the unique project in the Dutch professional journal Cement. After publication of my article, the Dutch Ministry of Infrastructure and Water Management contacted me to develop a UHPC overlay to solve the very serious fatigue problems of the large orthotropic steel bridge decks. Due to the increase of both the traffic intensity and the axle loads, which was not foreseen in the original design, premature fatigue cracks occurred. These cracks are initiated in the welds and the steel plates and resulted in decreased safety for the users. The problem was before solved by frequent inspection, local repair of cracks and resurfacing the deck plate with a new asphalt wearing course. Fatigue of orthotropic steel decks is a well-known problem worldwide and mainly related to the thickness of the deck plate. On the Moerdijk Bridge, the Kues asphalt wearing course had to be replaced every 5 years, and several kilometers of short cracks needed to be welded together again. This is not only very expensive, but also having impact on environment, transportation and mobility. Cracks occur on the underside of the deck plate, and if the crack becomes visible on the top side of the deck plate, then the crack is approximately 60 centimeters long. When there are several cracks in the deck plate in an area, the whole part of the deck plate needs to be replaced, and in that case, a supporting structure needs to be welded on the deck plate first to avoid deformations of the structure. After my proposal, including all the important details, the suggested bonded hybrid reinforced UHPC overlay has been tested during 4 years before a pilot project was executed in 2003. All tests and comparisons with other alternative strengthening methods showed very promising results, with the reduction of the stresses in fatigue critical details with a factor 4 until 5, and a potential extra service life of up to 50 or even 100 years. To replace the existing wearing course with the hybrid reinforced UHPC overlay, the bond between the steel deck plate and the overlay is of crucial importance to secure total deck stiffness and a uniform monolithic behavior under all circumstances. For that reason, the first investigations were focused on creating a bonding zone that met all requirements. A bonding zone can easily be created by connecting the mesh reinforcement and the steel deck plate by welded studs, but this might result in local peak stresses and potentially new cracks. This method turned out to be the use of a two-component epoxy-based adhesive with sprinkled-in bauxite aggregates. This resulted in a very good durable bonding strength of 4.8 megapascal and even 12.5 megapascal bonding strength in shear. Before applying the bonding zone, edge details were glued on the steel deck plate. After applying the bonding zone, the reinforcement is placed on rebars as spaces. The present reinforcement configuration is around 12 mm with a mass of 75. Placing of the UHPC on the first orthotropic steel bridge decks in 2005-2008 was done with the traditional double vibration screed. This is a complex method and is requiring many workers and supervisors on site. Later slip foam paves are used as a much more effective placing of the UHPC. Pouring, compacting, finishing and curing is done in a sequence. During the period 2005-2016, 9 large orthotropic steel bridge decks are strengthened with the hybrid reinforced UHPC overlay in the Netherlands. The same method is also investigated in Germany, and the first orthotropic steel bridge deck in Germany has been strengthened in 2009. Similar fatigue problems are known all over the world, and UHPC has been used for the strengthening of orthotropic steel bridge decks in Japan, China and Vietnam. Often welded studs are used to fixate the hybrid reinforced UHPC overlay on the deck plate. Experiences are not always positive. We also investigated the prefab method in 1999. and we placed the prefab panels in a wet epoxy glue to avoid welded shear studs. The prefab method with welded shear studs is now used to strengthen orthotropic steel bridges in France. The Eastern Scheldt storm surge barrier, built to avoid flooding in the parts of the Netherlands under sea level, which was inaugurated in 1986, has 62 sliding steel gates with a width of 41 meters and a height between 6 and 12 meters. During storm, the gates are closing to form a barrier against high water levels. The replacement of the 62 steel gates will be necessary because of the high additional cost of maintenance due to corrosion. Because of protection of the environment, waste of the repainting process is not allowed to come in the water of the Eastern Scheldt, and a construction needs to be built to avoid any spillage of material of the repainting process. An internal research project by the Civil Engineering Division is focused on the replacement with UHPC gates. To stay within the weight limitations of the hydraulic system to raise and lowering the gates, a UHPC gate is a very interesting alternative. The gates will be produced as prefab parts and connected with in situ cast UHPC joints on site close to the location.